Lights are on. OK. Thank you very much. I appreciate the opportunity to talk to everyone. And I'm going to be talking today about work that I've had a big part of, but has certainly been worked on by a lot of other people. And I'm going to start out by giving you a general overview of what intrinsics, metadata, and attributes are. And then I'm going to go through a number of these things that have been added recently and discuss how they can and should be used, some ways in which perhaps they shouldn't be used. And I will specifically touch on how Clang uses these in various regards. So let's go on. OK. Oh, that's what I said. And I may also say something about the future. I forgot about that. OK. So to start. So we have intrinsics, we have metadata, and we have attributes. So I have 3 overview slides for this. First, so what are intrinsics? So as many of you likely already know, intrinsics are things that you can call in the IR that have semantics that are defined by LLVM itself. And we have a number of these things. We've had them for a very long time. We have memcopy, and we have ads with overflows and things like this. And all of these things are intrinsics. They are not functions that are being called. They do not exist in any object file. They are expanded by the code generator or turned into something else. But LLVM itself has built-in understanding of what these functions mean. And many of them aren't actually functions that do anything. And in fact, I will be specifically discussing some more of these. For instance, we have intrinsics that designate the range where a particular value, a particular pointer value doesn't change, and then the end of the range where it doesn't change. Those functions don't actually do anything. They simply provide information to the optimizer. OK, attributes. So when you have a function, both the function itself, the function return value, and the function arguments can have these special additional properties. These are attributes. So here I have a very simple example. This example shows a function. It takes a pointer to some type that you can guess is a structure, although I don't show it on the slide. And it says byval on it. Well, what does that mean? Well, that means that, when the code generator actually materializes this function, this structure type is assumed to be passed by value. So the code generator will take that structure. It will allocate a new space for a new copy of it. It will copy the old data into the new, and then it will provide that to the function. Now, in the IR, you see this as a pointer to the structure, and you deal with it like a pointer. But it's a very special pointer, because it's a pointer that is in some sense owned by the callee. And so this is an example of an attribute, and I'll be discussing some more new attributes that we have for various things. And last but not least, we have metadata. So here again, I have an example of some metadata that we've had supported for quite some time. In this example, I think I copied all these examples out of regression tests, by the way, so they all have very nice names. And so this is an example for range metadata. And here you can see the range metadata says provides the optimizer information on the value being loaded by this load. So here we have a load. It is loading an 8-bit integer. And there's range metadata on that load that says that the value must be in between 0 or 2, where the ending number is not included. So it says essentially this number is guaranteed to be 0 or 1. And thus the optimizer can use that information to eliminate that pesky AND instruction that doesn't actually need to be there. OK, so now let me say something about some new things that we have. And they fall into these 3 categories. So there's an intrinsic, actually one intrinsic, so maybe I shouldn't have used the plural, but it is LLVM assume, which provides general assumptions to the optimizer. I'll talk about that. We have a number of new or quasi-new pieces of metadata. We have loop metadata. We have loop metadata that provide optimizer hints, which is sort of the first box. We have loop metadata that talks about loop carry dependencies, which is the second box. We have metadata that provides additional aliasing information. I'll mention that we've had metadata that provides aliasing information for a very long time because the type-based aliasing information, TBAA, has always been metadata. And this is new metadata that provides orthogonal information, likely. And lastly, we have a small piece of metadata that's called Nonnull. I'll talk about that. And also attributes. So we have an align attribute. Actually, we've had an align attribute for a very long time, but we now have new uses for the align attribute. We have a Nonnull attribute. We have a dereferenceable attribute. And below that, I've sort of broken out basically like what features in Clang cause these various things to be emitted. And I'll talk about that more as we go on. And I'm also going to talk about them in the order that is in the reverse of what I just said. And so here's why. So this is my diagram of how these various features can be used in terms of their expense in compile time and their potential impact on other optimizations. So first at the top, I have attributes. Attributes apply only to functions, function return values, function arguments, but they are essentially free. You may use them whenever you think they might apply. There's essentially no harm in doing so, I mean, aside from optimizer bugs and other things that may exist. So you can think of them as free. Now, then comes metadata. Now, metadata is sort of an interesting case. Metadata is not overly expensive. It generally doesn't interfere with optimization. But it's not really free. I mean, if you generate gobs and gobs of metadata, then you are going to slow down the optimizer as it has to process all of that stuff. And the way that metadata is stored and manipulated is generally in terms of strings and string maps and hash lookups and stuff. It's not really stored in the same memory locations as the objects to which it refers, so you have a lot of indirect pointer lookups as you're iterating through this stuff. And so you want to use metadata when you think it would be helpful, but you also say if you're doing a -0 code generation, if you care about compilation speed above optimization, then you certainly don't want to emit a lot of it. And then we'll come to intrinsics. So intrinsics, and especially this assumption intrinsic that I'll talk about later, they are really powerful. They can provide a lot of information to the optimizer in information that really can't be provided any other way. But it really can be expensive for several reasons. And primarily because the intrinsic looks like IR. It is IR. And that the value that you put into it has to be fed by other IR instructions. I mean, unless it's a constant, but then that's useless. So those instructions have a cost. They have to be processed by all the optimization passes. The optimization passes then have to take special care, some of them anyway, that do cost modeling have to take special care to ignore some of those instructions. And also, a lot of the optimizations, especially the people optimizations like those in intscombine, are predicated on checking that a value has only one user. Well, what if that value has a user that's now this assumption? So the optimization doesn't happen. Well, OK, so maybe that's good and maybe that's bad. So you have to be judicious in how you use this and make sure that it's actually worthwhile. And there are cases where it's worthwhile, but it's not always worthwhile, and you have to keep that in mind. OK, so now I'll go through these things at some speed. All right, so again, so here we have the align attribute. We've always had an align attribute, but it normally only applied to by-value arguments. Because when you created that special copy stack slot, you needed to make sure, you needed a way of designating what alignment that should have, because many ABIs specify that alignment, and it's not necessarily derivable from the type. So we've always had an align on that went along with by-val, and it was essentially ignored anywhere else. So one of these sort of really nice changes where the regression tests were much larger than the actual patch we fixed that so that the align could be specified on any pointer argument and would in fact convey to the optimizer that that pointer was guaranteed to have that particular alignment, which of course is still true for bival arguments, but is now can be true for anything else. And so Clang will now emit this in several cases. Primarily, it goes along with this alignvalue attribute, which I'll also talk about later. OK. So similarly, we have a non-null argument. You can have non-null on pointer pointer typed arguments. You can also have non-null on a pointer return value from a function, and it does what you would expect. So the optimizer can assume that the pointer is not null, checks against things that are, checks that a pointer is not null can then be eliminated, and it seems like, well, I mean, it really depends on the language as to how much this helps you or not. But surprisingly enough, it actually helps quite a bit in C++, where the language semantics dictate that the compiler insert null checks after certain kinds of allocations. And if you take your allocator function and you put one of these returns non-null attributes on it, then all of those can go away. And in fact, when we did this in LLVM, someone else did this, I did not. When we did this in LLVM, it turns out that you can speed up compilation time by almost 5% by getting rid of all of these checks. And that's the sort of self-hosting compilation speed. So it really can make quite a bit of a difference. OK. And so lastly, we have this dereferenceable attribute. So there are many cases where you know that pointers are dereferenceable. And why is this important? Well, it's important because when you know a pointer is dereferenceable, you know that a load of that pointer is safe to speculate. And when the pointer is safe to speculate, it means that if a load of a pointer is safe to speculate, it means that you can hoist it out of loops. And that's really where the benefit comes. So here I have an example which was derived from an actual benchmark that I had, so this is in C++, and we have this reference here to an integer c, and it is inside this loop. And before we had this dereferenceable attribute, and before Clang would emit it for references, we had a problem is that that c, right, that's a reference, right, so it's actually passed by pointer, and that pointer load could not be hoisted out of that loop. Because if you just have an arbitrary pointer that you don't know is dereferenceable, you could have passed it in null to that function. And it could also be the case that all ai is not greater than 0, and thus the pointer was never dereferenced, and everything was fine. And you can't change those semantics just because you want to hoist the pointer out of the loop. So you had a problem. And so the way we fixed this problem was to have an attribute that specifies that a pointer is dereferenceable, and the attribute takes the size. So it actually specifies the number of bytes that starting from that pointer value that are known to be dereferenceable. And Clang will now emit this for references, and it also emits them for this fairly obscure C99 feature, where if you have an array argument type and you put static in front of the size, that is also supposed to designate the same information, that the array is guaranteed to have at least that number of elements in it. And not many compilers do something with this, actually, but we do. So, and you can use this feature. It is quite useful for doing this kind of load hoisting. All right. So now I will start talking about some metadata. Now, one problem that we ran across was that we wanted some way of attaching metadata to loops. Well, it's sort of an odd concept in LLVM because LLVM doesn't have any kind of first-class loop construct. Loops are just sort of this implicit thing that happens, that just so happens because of certain kinds of control flow structures. So how do you attach metadata to a loop? Well, what we ended up doing was, at least for now, we have the sort of simplest thing that we could think of, which is that we attach the metadata to the branch on the back edge of the loop. And When you do that, you allow the metadata to refer to the loop. And so there are a number of optimizer hints that go along with this. So you can attach loop, like a loop ID metadata to a loop, and you can then specify hints like this loop should be unrolled by a certain amount, or fully unrolled, or it should be interleaved by a certain factor, or it should be vectorized, that kind of thing. And all of those hints are just that. They are hints. So they don't override the safety checks that normally go along with those optimizations. They simply override the cost heuristics. And I do want to point out one thing in this example, because it is relevant later. So if you have this first metadata entry here, it says !0. If you noticed, in the metadata itself is a list of metadata references, and the first metadata reference is itself. Now, it's sort of an odd thing, and this is used in TBA also. It is a way that in LLVM, this is the way that you create unique metadata. So you may have a problem, for example, that let's just say, for argument's sake, that you had two loops that you wanted to specify an unroll count of 4, and you didn't use this trick of self-referential metadata. So you would have, and all the metadata is unique by structure. So you never have two metadata values that are the same except for their identity. They don't have independent identity from their contents, I should say. And so you need, so if you had that and you had the same metadata attached to these two loops, and the enroller did something sensible, like once it unrolled the loop that said it should unroll the loop, it removed the metadata. So the next time it ran on the IR, it didn't unroll it again. If you didn't unique the metadata, when you removed that metadata, it would remove it everywhere, or it would change it. Right? Like if you changed the enroll count from 4 to 1 because you didn't want to unroll it again, now it would change everywhere on all the loops to which that was attached. And obviously, that's not the design that's wanted. So you need to create a unique reference. And the way that we create unique metadata references in LLVM is by creating self-referential metadata. So if you look at metadata, you will see this, and that's why it's there. OK, and just quickly, these are the hints that we currently have supported for vectorization and interleaving, et cetera. And Clang has a special pragma Clang loop, vectorize, interleave, et cetera, that can be applied in order to cause these to be attached to loops. OK, and I said those optimization hints don't say anything about safety. Here's the one piece of metadata we have that says something about safety. We have a parallel loop access metadata, which essentially asserts that the associated load or store memory access does not have any loop carry dependency. So in other words, if you have this metadata and you have it on all of the accesses in a loop, then we can conclude that the loop has no loop carry dependencies and can be vectorized. And that's what we do. So if you need a way of overriding the vectorizer's safety checks, and this is like like in the Intel compiler, you get like pragma ivdep, and in OpenMP we have this pragma OMP SIMD, which Clang now supports. And if you put the pragma OMP SIMD on top of a loop, it will cause this metadata to be emitted, and the vectorizer will vectorize it, even if it could not otherwise prove that there were no dependencies, et cetera. OK. So next, we're going to talk about aliasing metadata. Now, this is something like dear to my heart, since I've worked an awful lot on this. But and I'm going to skip forward in a minute and then come back to this slide after I do the example, because I couldn't put this and the example and everything on the same slide, so I apologize. But I will just to sort of briefly note the idea behind the aliasing metadata is that you can directly provide the sort of no alias graph in metadata. So if you have accesses and you know that those memory accesses don't alias, you now have a way of tagging those particular accesses and providing that information to LLVM's alias analysis passes, or alias analysis users, I should say. OK, and this is phrased in terms of aliasing scopes and domains of those scopes, and those are perhaps not optimal terminology, but I didn't think of anything better before developed. Now let me, so I'm going to go to the example, and then I'll go back and show you what the metadata looks like. And so here's the sort of primary use case in some sense, which is that, so we have this function. I wrote this in C because it's shorter than writing it in IR, but it has these restrict pointers. So restrict pointers on function arguments in C turn into no alias attributes on the IR. And we had a real problem with this kind of thing because you could provide this aliasing information, which was really important to, say, vectorizing loops inside this function. And then we would say, well, but the function is kind of small, so we'll inline it. And so we'd inline it, and the no alias attributes would go away because there's no function anymore, no arguments. And so the aliasing information goes away, and then we can't vectorize the loop. So it would have been better not to inline it, but obviously that's not really the kind of decision you want to make. And so it's better to preserve the aliasing information. Well, how are we going to do that? Well, so we have this metadata. And the way that we we use this metadata in order to preserve the aliasing information is essentially the following. Each of these restrict no alias pointers gets assigned an aliasing scope. So the aliasing scope means things that are derived from this pointer. And so each memory access can be tagged, optionally, with a scope, meaning I derive from that pointer. Or it could be tagged no alias to that scope, meaning I know I don't alias with stuff derived from that pointer. And so here, in this particular example, we would introduce two aliasing scopes, A and B, for argument's sake. And then we tag these various accesses. So for example, this access to C gets tagged no alias with A and B because it is not derived from A or B, and that's clear. The access to X, so X may be A and it may be B, and we're not sure which. So that gets tagged as alias scope A or B, and because it may be derived from A and it may be derived from B, and we're not sure. If we had an access purely to A, then it would be tagged as scope of A and no alias to B, because we know it is derived from A and we know it doesn't alias with B. And that's essentially how this works. Now, the actual algorithm is a bit more complicated because it has to also deal with capturing, because this sort of whether a pointer is derived from or based on another pointer can flow through external variables, and so you have to be a bit more careful about that. And it can flow through function calls, and the algorithm needs to deal with that. But nevertheless, this is the basic idea. Now I'll go back. So and I did copy most of this from the language reference, so which does have a little bit more explanatory text as well. So you don't have to take it all from this slide. But here I have some examples. So first we say, OK, so we have these two scope domains. And I'll mention quickly. Did I put this on the next slide? Yes. I mentioned that these scopes also have domains, and this is purely because of composability. So you put this aliasing information on these accesses because you want to inline this function and preserve the aliasing information. Then, well, what if the caller of that function also had no alias arguments, and that got inlined, and you need the metadata to apply in a composable way. So we have this concept of domains, which hopefully the language reference explains. And so the basic idea is that when you have two accesses, you want to check that for any given domain that applies to the scopes in those accesses, that the sort of set of things that you know you don't alias with is a subset, excuse me, is a superset of the set of things that the other guy may derive from. All right, so if you know that you don't alias with anything that guy might derive from, then you know you don't alias with that other pointer. And this is a sort of basic check that the aliasing analysis then does. All right. OK, so here's another easy one. We have non-null metadata. Now, non-null metadata also, it's like the range metadata. It applies to loads, but instead of applying to loads of integer types, it applies to loads of pointer types and says that the pointer isn't null. OK. So, and I suspect that we will end up adding similar metadata like this that corresponds to the other function attributes that apply to pointers like dereferenceable and no-alias and things. But so far we only have non-null. But that's the general scheme. And the thing to remember is that if you see non-null like this on a load, it's referring to the thing being loaded, not the pointer being loaded from. So I'm just pointing that out. OK. Now I'll talk about assumptions. So as I said, assumptions are really powerful. They can provide the optimizer with information on things that you know to be true that the optimizer otherwise has no other way of knowing. And it can do so in a very generic way. So it is an intrinsic. You get to call it with a condition, which is a Boolean, and you can form that Boolean in any way you want. Of course, the optimizer only recognizes certain kinds of information. So you can't get too fancy and have it do anything. But it recognizes a lot of stuff. And so in this particular example, as you can see, it's providing information about the alignment of that pointer. And it's true that if you take that code and you run it through ints combine, the alignment of that load will change from 4 to 32, for example. But the assumption will still stay, and that's because we only remove assumptions at the very end, right before code generation. And you want them to stick around because you want them to also apply to instructions from calls that are later inlined, or from if you inline this into its caller, for example. And so they're used by value tracking to pick up information on known bits and alignments, which is sort of the same thing. They can be used to feed known ranges into lazy value info, which is used by jump threading and other and SCCP. And they can be used to substitute for actual loop guards, and scalar evolution understands that. And there's more to come. And then we have an issue. Which causes us to have this concept called ephemeral values. So ephemeral values are things that we know will go away and will be free once we get to code generation. And this is important for things like inlining and loop unrolling, where you want to look at a function and get some estimate of how expensive it is. So let's just take this function, for example. If you didn't know that all those pointer to ints and ands and compares actually won't exist during code generation, you'd think that function is going to be a lot larger than it actually will be. So how do we deal with that? Well, so we have some utility functions in code metrics called collect ephemeral values, which can operate on loops and functions and various things, depending on what kind of path you have. Depends on which overload is most convenient. But the idea is that it will collect a list of all of these instructions that are going to go away, and then you can discount them when you do your cost analysis. And the inliner and the loop unroller and several other passes appropriately deal with this now. OK. And lastly, we have the assumption tracker. So now we have these assumptions, and we want to be able to use them when we're doing simplification. And now we also have sort of an issue, because you have to be able to find the assumptions that apply to any particular value. And the assumption that applies to a particular instruction might be far away in the entry block of the function, for example, not anywhere nearby. And so you have to have a way of efficiently finding them. So we ended up with this design where we have a special invariant analysis path called the assumption tracker. And the assumption tracker's job is to keep track of all the assumptions in a function. And what it does is that when you first ask it for the assumptions that are in a function, it will scan the function. It will keep a cache of the assumptions that it finds. And then and it keeps handles to those things. So if you remove them, they automatically get removed from the cache. But the one thing it can't do is it can't know if something gets added. So here there is a contract. for using assumptions. And the contract only applies to people who add assumptions. Not if you just want to use assumptions that are there. But if you write a transformation that adds assumptions, you must be aware of the contract. And the contract is that if you add assumptions, you need to register them with the assumption tracker. So here I have my the handshake. There's the contract. And it's important, so it gets a lightning bolt. Okay. And that's the one thing that you have to keep in mind. The other thing I'll mention is that if you're writing a transformation that's going to look for assumptions, then you do need to know if the assumption applies to a particular value, and that requires dominance information. But there is a utility function which goes through and does the appropriate computation for you. It's called isValidAssume for context. And you provide it the assumption that you found and the instruction you may want to simplify and some other things, and it will tell you whether you can use that or not. It takes account of dominance information. It also makes sure that you don't use the assumption in order to simplify its own ephemeral values, because normally that will just make the assumption trivially true and it will go away, and that's also not useful. Okay. So how is this used by Clang? Well, so we have a couple of different mechanisms. We have built-in assume, which is a sort of direct translation. We have all the sort of GCC-style alignment assumptions, which are intrinsics and also some function attributes. All those get translated into these things. We have the pragma OMP SIMD aligned attribute gets translated into these assumption intrinsics for pointer alignments. As you can see, I'm big on pointer alignments. We have the align value attribute, which I'll talk a little bit more on the next slide. If you have it on function arguments, it gets the align attribute. But if you have it in other places, when you do the L value to R value conversion, you get assumptions for the loads. Okay. And I want to say something about this align value attribute, because it's something that not many people are really familiar with. So the align value attribute is a GCC-style attribute, but is not supported by GCC. It actually came originally from a fairly recent version of the Intel compiler. And it was developed mainly, from what I understand, to meet the needs of HPC users. I have HPC users who have requested this. And so it's now been implemented in Clang and in LLVM in terms of this alignment assumption, intrinsic. And it solves the following problem. So let's just say you have a pointer and you want to say that the pointer, you know that the pointer is 64-byte aligned. Well, and you say, well, why do we need a new attribute for that? Because we already have an aligned attribute. And the problem is that there's no good way of using it. So the old way that you might try to do this, which people have tried to do, and it causes compilers to miscompile their code and then they complain, is that you say, well, I'm going to type def a sort of aligned double type. And so I have a type of double, and I say this type of double is always 64-byte aligned, and then I have a pointer to it, and everything seems fine because I have these two accesses, and the first one is loads from this 64-byte aligned double, and everything is happy, and then you have that second access to the next double in the array, and then the compiler likely miscompiles your code, and the user complains. Because you asserted that all those doubles were 64-byte aligned, and the next double in that array is clearly not. What? 8 bytes. Right. So, yeah, no, not a problem. Right, and so the align value attribute is the sort of thing that rescues this. Right? What you actually want is an attribute on the pointer type, not on the value, and in doing so, you can provide the correct information that is also semantically correct, and this ends up being quite important for vectorization and other things. So my talk is over, but I will spend about 30 seconds to mention a couple new things that are coming. There are more metadata that correspond to the attributes. We probably also want a way of tagging dereferenceable bytes where we know the size at runtime, but it's not a compile time constant. One of my highest priorities, actually, at this point, is getting Clang to emit the aliasing metadata for block-level restrict qualified pointers instead of just restrict qualified pointers on function attributes. There are many people whose work is reflected in this talk, And I thank them all, plus all the people who reviewed the patches and who supported them in other ways. And I have to thank the people who pay me, because that's also important, which is the Argonne Leadership Computing Facility, Argonne National Laboratory, and more generally, the Department of Energy. And that's the end, so thank you very much.
All right, questions?
I have actually more of a comment than a question at this point. But if you find yourself using assumes, please try to make sure that for folks who are working on this infrastructure know what you're doing with them. We're still working through what sort of the correct canonicalization for assumes and metadata and attributes are in all of these pieces. And knowing the various use cases is very important for that work.
I agree.
Other questions? All right, then. Well, let's thank our speaker.